Ever feel like the quantum world is this giant puzzle box full of fascinating but kind of intimidating mysteries?
Yeah.
Well, today we're grabbing our mathematical magnifying glass to look closer at one of those mysteries, path integrals. And don't worry, we've got this awesome guide, Joshua Lackman's paper, to lead the way.
What's so cool about this paper is it doesn't just throw around the term path integral and leave us hanging.
Right.
It actually gives us this really elegant way to define what these integrals are, especially in these special spaces called symplectic manifolds.
Okay, I'll admit, when I first saw symplectic manifolds on our agenda, I thought, whoa, we're going deep here. So for our listeners who haven't stumbled upon these yet, imagine a space where every single point has this built-in sense of rotation and stretching. Like picture a basketball spinning on someone's finger. That's got that symplectic vibe. But the truly mind-blowing thing is this paper actually connects these complex spaces to something way more familiar, antiderivatives.
Exactly.
Remember those from calculus?
It's such a clever link. Think about it. You've got a function, then its derivative, and then to go in reverse, you've got the antiderivative. Lackman uses a similar logic to define these path integrals.
So instead of just a regular derivative, we're dealing with this thing called a propagator. It sounds super sci-fi, but really it just describes how likely it is for a quantum particle to zip from one point to another. And Lackman's big move. He defines this propagator as a function that ticks off certain boxes related to its derivative, just like how we define antiderivatives.
You've got it. It's like hitting rewind on the whole derivative process, but in this wild quantum realm, it's a way to understand where a particle came from by looking at where it is and how it's moving.
So the propagator is like the quantum fingerprint of a particle's journey. But hold on, there's this other term that pops up in the paper, the Bergman kernel. Now this thing sounds seriously intimidating, like something out of Star Trek.
I promise it's not as scary as it sounds.
Yeah.
Think of the Bergman kernel as a sort of mathematical tool that's really good at understanding certain types of quantum spaces. And what Lackman found, which I think is absolutely amazing, is that when this Bergman kernel is constant along the diagonal, meaning it's got the same value at corresponding points, it basically hands us the path integral on a silver platter.
Wait, so this constancy thing, it's like finding a shortcut through a mathematical jungle. It just makes everything click into place.
It's even cooler than that. It's not just a shortcut. This constancy unlocks a deeper connection between different areas of math.
Wow.
Like suddenly realizing that two seemingly unrelated fields are actually speaking the same language. It's a big deal.
Okay, now my brain's officially tingling with curiosity.
Yeah.
So how does Lackman actually show this all working? Does he use any specific example?
He does. He dives into systems with what we call constant curvature. Imagine shapes like a flat plane, a sphere, or even a hyperbolic plane, which is kind of like a Pringles chick, all curved in on itself. He shows us exactly how to calculate the path integral for each of these cases, making the whole concept way more tangible.
So we're taking the theory for a test drive. What's really neat is how these examples show us that path integrals aren't always one size fits all. You can have different ways to describe the same quantum road trip, which is a bit like having different maps that all lead you to the same destination.
That's a really insightful observation. It speaks to the incredible flexibility and richness of this mathematical framework. But even with all these different paths, Lackman's approach helps us navigate through the potential confusion and extract meaningful insights.
To make sense of all these winding paths, he goes beyond the typical Riemann sums we learned about back in calculus class, right? He brings out the big guns, generalized Riemann sums.
Exactly. Because let's face it, things in the quantum world don't always travel in nice, predictable straight lines. Those particles are constantly zigging and zagging, taking the scenic route. So we need something more powerful than our regular Riemann sums to wrangle those integrals and make sense of the chaos.
So it's like we're swapping out our old compass for a state-of-the-art GPS to navigate this wild quantum terrain.
Love the analogy. And what's even more mind-blowing is how Lackman connects these generalized Riemann sums to even bigger concepts in mathematics.
Okay.
We're talking about things like deformation quantization and geometric quantization. These are like the high-powered telescopes mathematicians and physicists use to peer into the strange relationship between the classical world, where things are nice and predictable, and the quantum world, where it's all particles behaving like waves and probabilities instead of certainties.
Okay, so it's like Lackman is giving us this backstage pass to see the connections between these different mathematical approaches that might seem totally unrelated at first glance.
It's like he's revealing the hidden blueprint behind the scenes, showing us how these seemingly different structures are all part of the same grand design. And speaking of connections, there's another fascinating aspect of the paper. It touches on how this path, integral way of thinking, actually links back to the more traditional quantum mechanics we might have learned about with its operators and Hilbert spaces.
Right. I remember reading about that. It's like there are two different dialects for describing the same quantum reality. On the one hand, you've got the path integral approach, where we're summing up all those possible paths. And then there's the language of operators, which are like these mathematical instructions acting on quantum states in something called Hilbert space. It sounds super abstract.
It might sound abstract, but think of it this way. Hilbert space is like the grand stage where all the quantum action takes place. It's where we define the possible states a quantum system can be in. And operators, they're like the choreographers, dictating how those states can change and evolve over time.
So Lackman is showing us how to translate between these two quantum languages.
Precisely. He highlights how the propagator, that mathematical object we keep bumping into, acts as the bridge between these two worlds. It allows us to go from summing over paths to understanding how operators act on those quantum states.
It's like the propagator is the ultimate quantum translator. It helps us switch seamlessly between these different perspectives, depending on which one gives us the clearest view of the problem at hand.
Exactly. It's like having two different maps of the same city. One might be better for visualizing the overall layout, while the other might be more detailed for navigating specific streets. Having both maps just gives us a richer understanding of the city as a whole.
And in this case, the city is the mind-blowing world of quantum mechanics. But even with all these incredible insights, Lackman doesn't shy away from the big unanswered questions, does he? He leaves us with some pretty tantalizing mysteries to ponder.
He does. For example, remember how we talked about path integrals having multiple representations, different ways to describe the same quantum journey? Well, he raises this really intriguing question. Is there a single best propagator that satisfies certain special conditions? It's like searching for the most elegant and efficient way to translate between our two quantum languages.
That's a question that would definitely keep me up at night. And he poses another head-scratcher, right? Something about how these different ways of approximating path integrals, like those generalized Riemann sums we discussed, actually converge to the true value, especially when those quantum paths are going haywire.
That's right. Because, as we've been discussing, those quantum paths can be incredibly jumpy and erratic, almost like they're choosing their own adventure at every instant. So, understanding how our mathematical tools, like these approximations, handle that inherent quantum fuzziness is a really deep and important question.
It's like trying to, nail down a cloud. You can get close, but there's always this element of uncertainty and mystery.
Exactly. And that's what makes this whole field so exciting. It's like exploring uncharted territory where every new discovery leads to even more questions and possibilities.
It's definitely been a mind-bending journey, even for a deep dive. We've covered so much ground, from those familiar antiderivatives from our calculus days to these mind-boggling concepts like symplectic manifolds and generalized Riemann sums.
And through it all, we've seen how these seemingly abstract mathematical ideas actually give us this incredible power to describe and understand the behavior of the universe at its most fundamental level. That's the beauty of theoretical physics, isn't it? It's like we're uncovering the hidden code that makes reality tick.
Yeah, I'm walking away with this renewed sense of awe, not just for the vastness and complexity of the quantum world, but also for the ingenuity of the mathematicians and physicists who've developed these incredible tools to explore it.
Couldn't agree more. This paper by Lackman is a perfect example of that. How a single paper can open up entirely new ways of thinking about these fundamental concepts and push the boundaries of what we know.
So for our listeners who are feeling a bit like their brains have been put through a quantum blender, what would you say is the biggest takeaway? The one idea that should stick with them?
I think it's this. Path integrals aren't just some esoteric mathematical curiosity.
Right.
They're a powerful lens through which we can glimpse the hidden workings of the universe. They show us that the journey of a single particle isn't just about moving from point A to point B. It's about exploring all possible paths, all possible histories, all at once. And that, to me, is a truly mind-blowing and awe-inspiring idea.
Beautifully said. It's like that famous quote from Richard Feynman, one of the pioneers of path integral formulation. I think I can safely say that nobody understands quantum mechanics. But even if we don't fully grasp it, that doesn't mean we can't appreciate its elegance, its beauty, and its power to explain the world around us.
Absolutely. And who knows, maybe someday one of our listeners will be the one to make that next groundbreaking discovery, to finally crack the code of quantum mechanics wide open.
Now, wouldn't that be something? So to all our listeners, keep those brains buzzing, keep asking those big questions, and most importantly, keep exploring the universe, one path integral at a time.
Until next time, keep diving deep.
And that wraps up another deep dive. We'll catch you in the next episode, where we'll be tackling a whole new set of fascinating ideas and unraveling more mysteries together. Until then, happy exploring. Buckle up, everyone, because today we are diving headfirst into the wild world of quantum physics.
That's right. And more specifically,
we're talking about path integrals.
And
which, let's be honest,
we've got an expert on hand.
Can sound a little intimidating.
To guide us through this,
right.
It can get pretty complicated. We're going to break down how these path integrals actually work, specifically in the context of something called symplectic manifolds. And now, I know what you might be thinking, symplectic what?
Yeah, that sounds a little intense.
Right. But try to picture this. Imagine a perfectly smooth, frictionless billiards table, right?
Okay, I'm picturing it.
You hit a ball on this table, it always moves in these predictable ways. Well, symplectic manifolds are kind of like the mathematical versions of that billiards table, but instead of just describing how things move on a flat surface, they give us a way to describe motion within more abstract mathematical spaces.
Okay, I'm starting to get the picture. So no physics deep dive is complete without a paper to unpack.
Exactly.
And today we're diving into a mathematical definition of path integrals on symplectic manifolds.
Great paper.
Yeah. And it sounds like it's bringing some much-needed mathematical precision to this whole idea of path integrals, right?
Exactly. See, physicists absolutely love path integrals.
They're so useful.
Because they're incredibly useful for describing how quantum particles behave. But the math behind them, well, let's just say physicists and mathematicians don't always see eye to eye on what makes a rock-solid proof, you know?
So there's some, let's say, creative interpretation going on sometimes.
Exactly.
So is this paper trying to build a stronger bridge between the world of physics and the world of rigorous mathematics?
Exactly. And they start by doing something really clever. They make this link to something you might remember from calculus. The antiderivative.
Oh, yes, the good old antiderivative. Vaguely rings a bell. It's basically going in reverse from a derivative, right?
You got it. And what's so fascinating is that these authors, they draw this really cool parallel between finding antiderivatives and defining these path integrals.
Okay.
They suggest that, in a way, both of these things involve finding a function that satisfies certain conditions.
So with an antiderivative, you're looking for that function where if you take its derivative, it gives you back the original function. What about path integrals? What are we searching for there?
That's where this really cool concept called the propagator comes in.
A propagator, okay.
Yeah, and instead of finding a function, we're on the hunt for this propagator, which you can think of as like a special kind of quantum map. But instead of showing you roads and traffic like Google Maps,
right,
this map tells us how likely a particle is to travel between 2 points.
So not your typical GPS then. What makes this map quantum?
Well, because in the quantum world, particles, they don't just follow one route. They take every single path imaginable, all at the same time.
Hold on, they take every path at once. My brain just did a quantum jump,
yeah,
trying to imagine that.
It's mind-boggling, right?
It's like that particle has some serious FOMO fear of missing out on any possible route.
That's a great way to put it.
It can't decide.
And our propagator, it's like this super-powered quantum GPS diligently calculating the probability of finding that particle on each of those paths, no matter how crazy they might seem.
So we've got our particle pulling off some serious multitasking, exploring every possible path, and we've got this propagator keeping tabs on it all. What else does the paper tell us about how this propagator actually works? How does it manage to keep track of everything?
Well, it turns out this propagator, it's not just some free spirit, you know. This paper, it dives into the specific mathematical rules this propagator needs to follow.
Okay, so there's some order to this quantum madness.
Exactly. It gets pretty deep into the weeds. But the main idea is that not just any mathematical object can be a propagator.
Right. It's got to have the right stuff.
Yeah, it's got to meet some very specific criteria, and this is where things get even more interesting.
Okay, I'm intrigued.
Because the paper argues that to really make sense of this, we need to rethink a tool we thought we knew from calculus, the Riemann integral.
Okay, now you're bringing back some serious high school math flashbacks, Riemann sums, dividing things into tiny rectangles. I vaguely remember it.
You're on the right track. But here's the thing. That traditional way of calculating integrals, it works great when you've got smooth, well-behaved functions,
All right, nice and tidy.
But in the quantum world, those particles, they're not exactly known for being tidy.
They like to cause a little chaos.
Exactly. All those paths, all those possibilities, those neat little rectangles, they just can't keep up.
It's like trying to capture a hurricane with a butterfly net.
Precisely. We need a more powerful tool, something a bit more heavy-duty. So this paper, it actually proposes a more general definition of integration, one that can handle those wild quantum paths.
So instead of neat little rectangles, we're talking about some pretty abstract mathematical machinery to wrangle these paths.
Exactly. And to show you how this new approach works, they dive into some specific examples. Quantizing spaces like flat space, spheres, the hyperbolic plane, stuff we're a bit more familiar with.
Okay, so we're not just floating in this abstract mathematical void. There are concrete examples.
Absolutely. We've got to bring it back down to earth, right? And these examples, they reveal something really crucial. Propagators, they aren't necessarily unique.
So there's not just one true propagator.
It's not a one-size-fits-all situation, and that's a really important point.
So there could be multiple ways to describe the same quantum phenomenon, all equally valid.
Exactly. It's about finding the most elegant, the most useful way to describe what we're seeing. And to tell these different propagators apart, the paper zeroes in on a fascinating detail, the second-order Taylor expansion.
Okay, time for a quick refresher course.
Yeah.
What exactly is a second-order Taylor expansion again?
Right. So it's essentially a way to approximate a function. Think of it like taking snapshots of its behavior at a particular point.
Gotcha.
And what's interesting here is that the first-order expansion, which usually tells these functions apart, it's not enough for our quantum friends here.
We need to go deeper.
We need to go deeper to that second order. And the paper also talks about another cool approach called the lattice approach. Imagine dividing space into a grid, like pixels on a screen, and using that grid to approximate the path integral.
Okay, so back to discretization, breaking those paths into smaller, more manageable pieces.
Exactly. And this approach, it's especially helpful when dealing with those less predictable paths that traditional calculus struggles with.
So we've got all these different tools, different approaches, each with its own strengths. But why go to all this trouble? Why is it so important to understand these path integrals? It's like we've been handed this incredible toolbox, but we need the instruction manual to really grasp the power of what we're working with.
That's a great way to put it, and this is the really exciting part. We're not just talking about abstract math here. Path integrals and quantization, they're about understanding, like the essence of reality.
Okay, so this is about more than just equations on a page.
Way more. This is about understanding the universe at its most fundamental level.
So cracking the code of path integrals could unlock even bigger mysteries about the universe.
You got it. And what's really cool is that this paper, it doesn't just introduce its own approach. It connects the dots between what they're doing and other established methods. We're talking Toeplitz quantization, even Koncevich's deformation quantization, stuff that can sound super complicated, but it's like finding these hidden pathways between different parts of physics and math.
So it's like we have all these brilliant minds working on different pieces of the puzzle, and this paper is revealing a secret passage that connects them all.
Exactly. And that's what makes this so exciting, finding this underlying unity between ideas that might seem totally separate at first glance.
I love how this deep dive has not only shown us just how complex the quantum world is, but also how elegant and interconnected the math we use to describe it can be. It's pretty mind-blowing.
Absolutely. And it leaves us with a pretty big question, too. You see, the paper, it mainly focuses on spaces with very specific properties. But what if we could use this mathematical framework to describe even more complex spaces, like maybe even the fabric of space-time itself?
Now, that is a thought to leave us pondering. It seems like even in the quantum world, there's always something new to explore. And that's what makes these deep dives so fascinating. Well, on that note, we're going to have to wrap up this deep dive for today. But I have a feeling the questions it sparked will stay with us long after this episode ends. Thanks for joining us, everyone, and we'll see you next time for another adventure into the world of science and mathematics.
Ever get that feeling?
Feeling like what?
Like you're standing at the edge of something huge.
Yeah. Okay.
And mysterious.
Okay.
Yeah?
I think I know that feeling, yeah.
Today, we are diving headfirst into one of those mysteries.
Okay.
The world of quantum mechanics
All right.
And something called path integrals.
And believe me,
Okay.
these are not the integrals you remember from calculus class.
Okay.
We're talking about a whole new way of looking at how things move.
Right.
On a quantum level.
This is the kind of stuff that can make your head spin.
Yeah.
But that's what we do here at the Deep Dive.
That's right.
We break it down.
Right.
So you can impress your friends.
Yeah.
With your knowledge of all things quantum.
All the quantum strangeness.
So to start, can you give us a quick explanation of what a path integral even is?
Okay, so imagine for a second that you're not bound by the usual rules of reality.
Okay.
As a quantum particle.
Mm-hmm.
You don't just take one path from point A to point B.
Right.
Instead, you take every path imaginable.
Oh, wow.
All at the same time.
Okay.
Each with its own little wave of probability.
Mm-hmm.
Path integral tries to add up all those possibilities.
Okay, so let's unpack that a bit.
Yeah.
It's like every what-if scenario in the universe is playing out simultaneously for this tiny particle.
Yeah.
That's both incredible and incredibly complex.
It is.
And that's where our friend Joshua Lackman comes in, right?
He does.
This new paper,
Yeah.
He's trying to bring some mathematical clarity to this crazy concept.
Exactly.
Yeah.
Lackman's paper focuses on a more mathematically rigorous way to define path integrals.
Okay.
Especially those used in a specific area of physics
Mm-hmm.
called symplectic manifolds.
Symplectic manifolds. Okay, that sounds a little intimidating. Can you break that down for us?
Think it like this.
Yeah.
If quantum mechanics is a play,
Okay.
symplectic manifolds are the stage where all the action happens.
Got it.
They have a specific kind of geometric structure
Mm-hmm.
that's crucial for describing how physical systems
Right.
evolve over time.
So it's like the backdrop of reality itself. In a way, yeah. And Lackman is trying to figure out the rules of the road within that backdrop.
He is.
He even makes a fascinating comparison
Yeah.
to something we might remember from calculus.
Right.
The antiderivative.
What's so cool is that Lackman isn't just trying to find the answer to a specific path integral.
Okay.
He's looking for a function,
Right.
the path integral itself,
Mm-hmm.
that fits certain properties
Okay.
related to a given physical field.
So it's like he's not just trying to solve a single equation.
Right.
He's trying to crack the code of the entire system.
You got it.
Amazing.
And the function he's after, this propagator,
Mm-hmm.
essentially tells us the probability amplitude
Okay.
of our quantum particle,
Right.
moving from one point to another.
Okay.
Think of it as a map of all the potential journeys our particle could take.
It's a pretty powerful map.
Is.
And by looking at the path integral this way,
Yeah.
we can start to see it less as a vague concept
Right?
and more as a concrete mathematical object.
Yeah.
One we can really get our heads around.
Exactly.
Okay.
And that leads us to another fascinating concept.
Okay.
Coherent states.
All right, before we go any further,
Yeah.
coherent states.
Yeah.
Can we get a quick explanation?
Sure.
For those of us who haven't quite gotten our PhDs in quantum optics.
Think of coherent states as the closest a quantum system can get
Okay.
to acting like something we see in everyday life.
Okay.
They're kind of like little pockets of order within the chaotic quantum world.
So a bit of sanity amidst the madness.
You could say that.
And Lackman's approach just naturally leads to these coherent states.
It does.
Yeah, it's the connection.
It turns out that working with coherent states leads us to a specific type of space
Okay.
called a Kähler manifold.
Of course it does.
Of course.
Because why make things simple, right?
Why would we?
In all seriousness, what makes Kähler manifolds so important here?
Think of them like spaces
Okay.
with a unique geometric structure
Mm-hmm.
that makes calculations in quantum mechanics much easier.
So it makes it a little bit simpler.
Yeah, they're like having the right tools for the job.
Got it.
Many easily computable examples of path integrals come from these Kähler manifolds.
So these manifolds give us a sort of testing ground
Right, Dick.
for these complex quantum ideas.
Yeah.
And speaking of tools, Lackman uses this thing called the Bergman kernel.
Right.
It sounds pretty intense.
This is a powerful mathematical tool
Yeah.
that helps us both construct and analyze these complex path integrals on Kähler manifolds.
Right.
It's like having a special lens that lets us look deeper into the quantum world.
It's amazing how this paper connects all these different mathematical ideas.
It is, yeah.
But we have to remember
Yes.
that our usual ways of calculating integrals just won't cut it with path integrals.
They won't.
It's like trying to map a network of lightning strikes using straight lines.
That's a good way to put it.
Right.
Yeah, traditional methods like Riemann sums are great for a lot of things,
Mm-hmm.
but they just can't handle the wild,
Right.
unpredictable nature of quantum paths.
So how do we even begin to deal with these paths that are anything but straight and narrow?
Well, Lackman has an idea.
Lackman must have something up his sleeve to handle this, right?
He does. He uses a more sophisticated version of the Riemann integral.
Okay.
That can handle all the twists and turns of those crazy quantum paths. It's a version specifically designed to behave well under what we call pullbacks in mathematics.
Okay.
It's a bit of a brain twister.
Right.
But it allows him to create a much more robust way of dealing with path integration.
It sounds like he's creating a whole new set of mathematical tools.
He is.
Specifically designed to explore the quantum world.
Yeah, that's a great way to put it.
To put these tools to the test.
Yes.
He applies them to some pretty fundamental shapes, right?
You got it. He uses his method to calculate path integrals on shapes with constant curvature.
Okay.
We're talking about flat spaces, spheres, and hyperbolic planes.
Okay.
Some of the basic building blocks of geometry.
These shapes are like the test dummies of the geometry world.
Right.
What's the point of exploring these shapes in the context of path integrals?
They provide a kind of controlled environment for Lackman to test out his ideas.
Makes sense.
And when he applies his definition to these shapes, something really interesting happens.
What's that?
He finds connections to earlier work by two physicists,
Okay.
Toeplitz and Kähler.
Okay, now we're talking about some big names in physics.
We are.
What's the connection?
Yeah.
Does Lackman's work support their findings or contradict them?
What's incredible is that Lackman's definition of path integrals actually lines up perfectly.
Wow.
With the results that Toeplitz and Kähler found.
Okay.
Using completely different methods.
It's always reassuring when different paths lead to the same destination.
It is.
It gives you that feeling that you're on the right track.
It really does. But what's even more fascinating is that Lackman doesn't stop there.
Of course not.
His work also starts to bridge the gap between two very different ways of looking at quantum mechanics.
Okay.
Deformation quantization.
Okay.
And geometric quantization.
Okay. I have a feeling this is a pretty big deal.
It is a big deal.
Can you break those down for us?
Yeah.
What are these different types of quantization?
So.
And how does Lackman's work fit in?
Well, in the simplest terms, quantization is how we take a system from the world of classical physics to the world of quantum physics.
Got it.
It's like translating between two different languages.
Right.
Deformation quantization uses algebraic methods to do this, while geometric quantization relies on geometric structures.
So two different approaches to the same problem.
Exactly.
And Lackman is finding some common ground between them.
Exactly. His work suggests that these two approaches might not be as different as they seem.
Wow.
It's like he's found a hidden passage connecting two seemingly separate rooms in the quantum house.
This is already blowing my mind.
Yeah.
And we're just getting started.
Just getting started. It's pretty amazing, isn't it?
What's that?
How these seemingly abstract mathematical concepts can have real implications for how we understand the universe, you know?
Absolutely. But it can be hard to see the forest for the trees sometimes.
Yeah.
What does this new perspective on path integrals actually tell us about the universe?
Well, for one thing, this new definition gives us a much more solid mathematical foundation for something that's been notoriously tricky to pin down.
So no more hand-waving and saying,
right,
it just works. Trust us.
Right, exactly. Lackman is all about clarity and precision.
Okay.
But it goes deeper than that.
Okay.
His work could potentially bridge the gap between the smooth, predictable world of classical physics and the fuzzy, uncertain world of quantum mechanics.
Okay, now we're getting to the good stuff. That gap has been a head-scratcher for physicists for ages.
It has.
How does Lackman's work even begin to address that?
Remember how we talked about the propagator earlier?
The
function that maps out all the possible journeys?
Yep, like the quantum itinerary.
Right.
Okay.
By analyzing the behavior of this propagator as it moves from point A to point B, we can start to see hints of how the familiar world of classical physics might emerge from the weirdness of the quantum world.
So it's like zooming out from a blurry image and seeing a sharper picture emerge.
That's a great way to put it.
Right.
It's about finding those hidden connections, those subtle links between the quantum and the classical. And if we can truly understand those links, we might finally be able to reconcile those two seemingly incompatible views of reality.
That's a pretty mind-blowing thought.
It is.
But let's bring it back down to earth for a minute and talk about those specific examples Lackman uses in his paper.
Okay.
He spends a lot of time talking about surfaces with constant curvature.
He does.
What's the significance of those shapes?
Well, those shapes, things like flat planes, spheres, and hyperbolic planes, are like simplified models of more complex spaces.
Okay.
They allow Lackman to really dig into the nitty-gritty of his definition.
So it's like using a flight simulator.
Exactly.
To test out maneuvers before flying a real plane.
And through these examples, Lackman shows us
that
his definition isn't just some abstract mathematical idea.
Right.
It actually produces results that align with what we've seen using other methods.
Right.
Like those from Toeplitz and Kähler.
Again, it's always nice when different paths lead to the same destination.
It is reasonable.
It gives you that sense of confidence in the results.
Absolutely. But what really gets me excited is how Lackman takes it a step further.
Okay.
By connecting his work back to those two big frameworks in quantum mechanics.
Right.
Deformation, quantization.
Right. Those two different approaches to quantizing a system.
Right.
Essentially translating from the language of classical physics to the language of quantum physics.
Exactly.
Okay.
And you remember how deformation quantization uses algebra, while geometric quantization uses geometry.
Yep. Two very different toolboxes for tackling the same problem.
Right. And they've always seemed like completely separate approaches.
Right.
But Lackman's work hints at a deeper connection.
Okay.
Like there's a hidden unity underlying both of them.
So it's like these two approaches have been speaking different dialects of the same language all along.
That's a great way to look at it, yeah.
And Lackman is starting to piece together the common tongue.
Exactly. It's like having a Rosetta Stone for quantum mechanics. By looking at these different quantization schemes through the lens of his new definition of path integrals, Lackman is revealing a deeper level of understanding.
Okay.
A more fundamental framework that could tie everything together.
Wow. That's a pretty bold claim.
It is.
If he's right.
Yeah.
This could have major consequences for how we understand quantization as a whole.
Absolutely. His work is opening up entirely new avenues for research.
Wow.
New ways of thinking about some of the most fundamental problems in physics.
It's like he's kicked open a door that was bolted shut.
Right.
And now we have a whole new world of possibilities to explore.
And speaking of exploring new worlds, let's not forget about those symplectic manifolds.
Ah, yes. Those special spaces that are so crucial to all of this.
Right.
Can you remind us again why those are so important?
Remember how we said that they have this unique geometric structure?
Yes.
Well, it turns out that this structure makes them perfect for describing classical mechanics.
Right.
It's almost like these manifolds have the classical world built into their very fabric.
So it's like they provide a natural bridge.
Like a bridge,
between the classical world and the quantum world.
Exactly. Yeah, that's a great way to think about it.
Right.
And what Lackman has done is provide a more rigorous way to describe how we move from that classical world embedded within these manifolds to the quantum world.
It's like he's built this incredible bridge between two different realms using the language of geometry.
It is like that.
And speaking of bridges.
One of the things I found most fascinating about this paper is how it highlights the limitations of our traditional mathematical tools. It's like Lackman is saying, hey, if we're going to explore the quantum world, we need better maps.
We need better maps, exactly.
Right.
He makes a really compelling case that traditional Riemann integrals while perfectly adequate for most things, just can't keep up with the weirdness of quantum paths.
Right. It's like trying to measure the coastline of England.
Right.
You can get a rough estimate.
Yeah.
But the closer you look,
the
more twists and turns you see.
You see more. Yeah.
And the longer that coastline gets,
the longer it gets, right?
Quantum paths are kind of like that. They're full of these strange jumps and zigzags.
Right.
That just don't make sense in classical physics.
Right.
And that's where Lackman's generalized Riemann integral comes in.
Right.
It's specifically designed to handle all those crazy quantum twists and turns.
It's like he's invented a whole new type of measuring stick.
He has.
One that can bend and flex to accommodate the quirks of the quantum realm.
Exactly. It can handle it.
But it's not just about having the right tools, is it?
It's not, no.
It's about understanding why those tools are necessary.
It is.
What's the deeper significance here?
You're absolutely right.
Yeah.
Lackman makes a really important point about needing to consider higher order information.
Okay.
About these quantum paths.
Okay.
It's not enough to just look at where a particle starts and where it ends up.
Right.
We need to understand the journey in between.
Right.
All the strange detours and jumps along the way.
It's like the difference between looking at a map of a city and actually walking those streets.
Right.
The map gives you a general sense of things.
Yeah.
But the real experience is in the details.
Right.
Those unexpected turns and hidden alleyways.
What a fantastic analogy.
Right.
And just like those city streets.
Yeah.
Each twist and turn in a quantum path.
Yeah.
Carries crucial information.
Right.
Information that traditional integrals just can't capture.
Which is why Lackman's work is so exciting.
It is, yeah.
He's not just giving us a new mathematical tool.
Right, yeah.
He's giving us a whole new way of looking at the quantum world.
He is. It's a whole new perspective.
It's mind-blowing how a seemingly abstract concept, like a generalized integral,
I know, right?
can have such profound implications.
It really speaks to the power of mathematics.
Yeah.
As a language.
Right.
A way of unlocking the secrets of the universe.
Wow.
And Lackman has given us a new dialect.
Right.
A way to communicate with the quantum world on its own terms.
And who knows what we might discover when we can finally understand that language.
Who knows? The possibilities are endless.
It's like a whole new world of possibilities has opened up.
A whole new world, yeah.
And I, for one, can't wait to see where this leads.
Me neither. This paper raises so many exciting questions.
It does?
It really feels like we're on the verge of something.
Yeah.
Truly groundbreaking.
Absolutely. Well, sadly, that's all the time we have for today's deep dive into the incredible world of path integrals.
Of course.
And Joshua Lackman's groundbreaking work.
It was a great paper.
We've covered a lot of ground today.
Yeah.
From rethinking the very foundations of calculus
Right.
to exploring the hidden connections between different areas of quantum mechanics.
It's all connected.
We hope this episode has left you with a sense of wonder.
I hope so.
A thirst for more knowledge,
Yeah.
and perhaps even a little bit of that mind-blown feeling.
A little bit.
That keeps us all coming back for more.
Keeps us coming back for more.
Until next time, keep exploring, keep questioning,
Absolutely.
and keep diving deep.
Dive deep. Welcome to the Deep Dive. Today, we're going to be strapping on our theoretical physics helmets and diving headfirst into the mind-bending world of quantum mechanics.
Always a thrilling journey.
Isn't it?
Yeah.
And, we're going to be unpacking this dense research paper, a mathematical definition of path integrals on symplectic manifolds. And let me tell you, it's a wild ride through some seriously advanced math. But trust us, the insights are worth it. You ready to have your mind blown?
Let's do it.
Okay, so the paper dives right into this thing called path integrals. It's basically a way physicists trying to describe how particles move in the quantum world. Now, in our everyday world, if you throw a ball, it follows a nice predictable path, right?
Right, classical physics, straightforward stuff.
Exactly. But in the quantum realm, things get a lot weirder. Instead of neatly following a single path, these tiny particles are like, nah, we're taking all the paths at the same time.
It's true. Quantum particles are a rebellious bunch. This paper uses a clever analogy to help us wrap our heads around this concept. They compare path integrals to finding antiderivatives in calculus.
Okay, flashback to calculus class. Not always the fondest memories for some of us.
Yeah.
But I'm intrigued. How does that even relate?
Well, imagine you have a derivative which tells you about the slope of a curve. To find the antiderivative, you're essentially trying to figure out all the possible original curves that could have that derivative. The paper points out that this process is similar to figuring out all the possible paths a quantum particle might take.
So instead of paths on a graph, we're talking about paths a particle can take through space and time. Even if those paths get super weird and defy our usual logic.
You got it. And this is where the analogy gets even more interesting. The paper emphasizes that path integrals in quantum mechanics aren't always as straightforward as finding a nice, neat antiderivative.
Why is that? Are quantum particles just really bad at following directions?
You could say that the rules governing the quantum world are inherently probabilistic, meaning we can't pinpoint a particle's exact path with 100% certainty. It's like trying to predict the exact path of a leaf floating on a turbulent stream.
Okay, so things just got really complex. So how does this paper tackle this problem?
This is where they introduce a key player, coherent states. Think of them as a bridge between the bizarre quantum world and our regular intuitive understanding of physics.
So they help us make sense of the quantum chaos.
Exactly. In the quantum world, Particles are often described by wave functions, these fuzzy clouds of probability. Coherent states, however, are special. They're like the most well-behaved kids in a chaotic classroom, still bound by quantum rules, but exhibiting some properties that resemble classical particles. They help us bring some semblance of order to the quantum madness.
Fascinating. So how do these coherent states actually help with those tricky path integral calculations?
Well, that's where things get really interesting. The researchers found that when dealing with systems that have specific geometric properties, and bear with me here, we're talking about mathematical concepts like symplectic and Kähler manifolds.
Now, those sound intimidating.
They are some pretty advanced mathematical concepts, but don't get too hung up on the terminology. Just imagine them as specific types of geometric spaces, like a sphere or a saddle shape that have unique properties.
Okay, so specific shapes in a way.
Exactly. They found that in these specific geometric settings, the path integral calculations become more manageable.
Interesting. So the shape of the space actually influences the math.
Precisely. It's like the geometry provides a framework or a scaffold that helps to simplify the calculations.
That's mind-blowing. It's like the universe is giving us a hint saying, hey, use this shape. It'll make the math way more elegant.
I like that. And it's not just about simplifying the math. These findings offer a glimpse into the potential for a deep connection between geometry and quantum mechanics, a connection that might reveal something fundamental about the universe itself.
Okay, now we're talking. This is what gets me excited, starting with a seemingly abstract mathematical concept and ending up with insights into the fabric of reality. But how exactly did they test this out?
They applied their ideas to some specific examples. Flat space, which you can think of as your everyday intuitive understanding of space, a sphere, which is pretty self-explanatory, and something called a hyperbolic plane.
Okay, now hold on. A hyperbolic plane, you're going to have to elaborate on that word.
Think of it like a saddle shape that extends infinitely in all directions. Picture a Pringles chip, that curved shape, but stretching out forever.
Okay, I can kind of visualize that.
Good. Now, what they found when they applied their method to these specific geometric spaces is that the path integral calculations became much more manageable. It was like the specific geometric properties of each space provided a sort of framework that helped to simplify the complexity.
So it's like each of these shapes has its own set of rules that make the quantum math a bit more well-behaved.
Exactly. It suggests that there might be a deep-rooted connection between geometry and quantum mechanics, a connection that could help us unlock a deeper understanding of the universe. What's fascinating is that this connection between geometry and quantum mechanics isn't entirely new territory. Physicists and mathematicians have been grappling with these ideas for decades, and this paper does a great job of building on those existing frameworks.
Oh, so there are even bigger ideas at play here. Tell me more.
Absolutely. The paper connects its findings to broader mathematical concepts like deformation quantization and geometric quantization. These are admittedly pretty dense terms, but they represent different ways mathematicians try to make sense of the quantum world using the language of geometry.
Okay, so it's like using one toolset, geometry, to understand another, quantum mechanics.
Exactly. Think of deformation quantization, like trying to gently reshape or deform our classical understanding of physics to accommodate those strange quantum rules. It's like taking a familiar object and subtly warping it to fit into a whole new system.
So giving classical physics a bit of a quantum makeover.
Precisely. Now, geometric quantization takes a different approach. Instead of tweaking classical mechanics, tries to build a quantum theory from the ground up, using geometric properties as its building blocks.
Interesting. So different approaches, but with a shared language. That's pretty neat. And this paper manages to touch on both of these bigger concepts.
That's what makes it so compelling. It's not just solving one isolated problem. It's finding connections between different areas of mathematics and physics, pushing the boundaries of our understanding. And here's the really exciting part. The paper doesn't just give us answers. It opens up a whole new avenue for exploration, raising more questions than it answers.
You know me, I love a good mystery. What kind of questions are we left with?
Well, for one, this research shows us how powerful the right mathematical tools can be for unraveling the mysteries of quantum physics. But it also begs the question, are there even more elegant, more fundamental ways to grasp the essence of path integrals? Perhaps using geometric ideas we haven't even begun to explore.
It's like we've climbed this incredible mathematical mountain, and just as we reach the summit, we see an entirely new mountain range stretching out before us.
A perfect analogy, and that's the beauty of cutting-edge research. It constantly reminds us of the vastness of what we don't know, sparking our curiosity to explore further.
It's inspiring, really. It reminds us that even in the most mind-boggling realms of theoretical physics, There's always more to learn, more beauty to uncover, more mysteries to unravel. And this journey all started with this single research paper.
This paper was our launch pad, but the exploration doesn't end here.
Exactly. So for all you listeners out there, this is where we challenge you to keep digging, keep questioning, keep diving deeper into the mysteries that surround us. Who knows what incredible connections and breakthroughs await? You know, it's funny. We started by talking about these like tiny particles in the quantum world, and somehow we ended up like contemplating the entire universe.
That's the beauty of theoretical physics, right? It takes us on these incredible journeys connecting the smallest pieces of the universe to the biggest questions imaginable.
It really is humbling, and this paper has definitely left me with this sense of awe, but also kind of a thirst for more.
Yeah.
You know, it's like we've only just scratched the surface of what's possible with these mathematical tools and the insights they might unlock.
I completely agree. And that's what I find so inspiring about research like this. It doesn't just give us answers. It illuminates how much more there is to discover. It reminds us that the pursuit of knowledge is an ongoing adventure.
Exactly. And for all you listeners out there, we hope this deep dive has sparked your own sense of wonder and inspired you to continue exploring the mysteries of the universe. After all, that's what the deep dive is all about. Until next time. All right, get ready to explore the quantum realm, because today we're tackling this paper you sent on a mathematical definition of path integrals on symplectic manifolds.
Oh, this is going to be fun.
It's definitely a wild ride through some dense math, but that's what we do here, right? We unpack it all and try to make sense of these coherent state path integrals.
Exactly. And what's really interesting here is that we're dealing with a different way of thinking about quantum mechanics itself.
Okay, I'm intrigued.
You see, this paper is all about putting together a really, really rigorous mathematical framework for path integrals.
And they're specifically looking at these coherent state path integrals, right?
Yes. And those have some really cool properties.
So for anyone who might not be familiar with them, can you give us a quick rundown on what path integrals are in the first place?
Okay, so imagine a particle, right? And it needs to go from point A to point B.
Got it.
In classical physics, we just figure out the simplest path it takes.
Makes sense.
But in the quantum world, it gets weird.
Of course it does. It's quantum.
Yeah, path integrals basically say we have to look at every single path that particle could take.
Like every twist, turn, every crazy detour.
Every single one, even the ones that seem impossible.
So even a quick trip to another dimension and back.
Exactly. Each path gets what we call an amplitude, which is like a measure of how likely that path is.
Okay.
Then we add up the amplitudes for all those crazy paths, and that gives us the probability that the particle actually moved from A to B.
So it's like the universe is trying out every single option at the same time.
That's a great way to put it. It's like the universe is a terrible multitasker.
Huh. I like that analogy.
But that's just the tip of the iceberg.
Okay, because this paper, it dives into coherent state path integrals.
Right.
And how do those differ from, you know, your standard path integral?
Well, think of it this way. Feynman's path integrals, those are like using a regular map to get around.
Okay, I see where you're going with this.
You see all the streets and roads, everything.
Okay.
But these coherent state path integrals, they're more like using a map that just focuses on specific landmarks.
Interesting.
These coherent states, they're like those landmarks.
Got it. So it's like highlighting the important intersections, the key points along the way.
Yes. Exactly. And what this paper does is it digs into how these coherent state path integrals aren't just some mathematical quirk.
There's more to it than that.
Oh, yeah. They're connected to all sorts of other areas in physics and math, like the ways we go from classical physics to quantum mechanics.
We're talking about those quantization schemes.
You got it. And this is where it gets really exciting.
Okay, lay it on me.
This paper shows us how certain geometric spaces, these Kähler manifolds, they're perfect for calculating these coherent state path integrals.
Hold on. Kähler manifolds. Those sound a bit intimidating.
They sound complicated, but the basic idea is pretty straightforward.
Okay, good.
Imagine a smooth, curved surface, like a sphere.
Okay, I can picture that.
But this surface, it also has a way to measure distances and angles built right in.
Like it has its own cosmic ruler and protractor.
Exactly. That's basically what a Kähler manifold is.
Huh, interesting.
And they're everywhere in physics. In this case, they give us a really elegant way to think about those abstract phase spaces where every point describes both the position and the momentum of a particle.
And that's crucial in the quantum world, right? Knowing where a particle is and where it's going.
Precisely. We need both those pieces of information because things are so unpredictable at that level.
Right. It's all about probabilities and uncertainties.
Exactly. And to help us out with all this, we had this thing called the Bergman kernel.
Okay, hit me with that one.
So the Bergman kernel is like a special lens that lets us analyze these Kähler manifolds in a way that's directly related to the quantum mechanics we're trying to understand.
So it connects the geometry of those spaces to the behavior of quantum particles.
Exactly. It's a powerful tool.
It sounds like we're just getting started, and my brain is already doing backflips.
Well, hold on tight because it's about to get even wilder.
Oh boy, I can't wait.
This paper, it actually uses a really interesting analogy to explain this whole approach, the idea of an antiderivative from calculus.
Okay, now you're talking my language.
So you remember what an antiderivative is, right?
Vaguely. It's been a while since calculus class.
Well, it's basically like going in reverse from a derivative.
Right. Finding the original function that gave you that derivative.
You got it. And in a way, finding a path integral can be thought of as being similar to finding an antiderivative.
Okay, I see what you mean.
But instead of regular functions, we're dealing with these more abstract things called measures on all the possible paths.
Measures. Like how much stuff is contained within a set of paths.
That's a really good way to think about it. And the derivative of this measure, in a very loose sense, should lead us back to the core physics, to what's really going on with those path integrals.
So it's like we're trying to uncover the hidden blueprint behind those quantum paths.
Precisely. But here's the catch, and the paper actually points this out too.
What's the catch?
This analogy, while helpful, it has its limitations.
How so?
Well, think about a typical antiderivative problem.
Yep.
Usually there's just one right answer, right?
Yeah, that's kind of the point.
But path integrals, they're not as straightforward.
Oh.
You can actually end up with multiple solutions that seem perfectly valid, which makes things a bit tricky when we try to interpret what the math is telling us about reality.
So it's not that the math is wrong. It's just that it might offer us different, equally valid perspectives on the same quantum phenomenon.
That's the heart of it. It's like looking through a kaleidoscope. You see different patterns depending on how you turn it, but they're all generated by the same underlying structure.
Wow, that's a really cool way to visualize it.
And to make things even more interesting, the paper actually highlights how important the second derivative is in all of this.
The second derivative. Now we're really going deep into calculus territory.
I know, right? But there's a good reason for it.
I hope so.
It turns out that to get the right answer, we need to go beyond just the first derivative and really delve into what the second derivative is telling us.
And what exactly is the second derivative telling us in this context?
That's the really intriguing part. It hints at the strangeness of the quantum world.
How so?
Well, in your normal calculus class, the second derivative tells you about the curvature of a function, right? How much it's bending.
Right, like how much a curve is curving.
Exactly. But here, it's suggesting something much weirder.
Like what?
The paths we're dealing with, they're not those smooth curves you see in textbooks.
They're not.
No. They're more like jagged, fractal-like lines that are constantly changing direction.
So the second derivative helps us capture that quantumness, that inherent jitteriness of the quantum world.
Exactly. And it's this inherent strangeness that makes this whole area of physics so captivating.
I can definitely see why. So we've got these coherent state path integrals, and they're already bending our minds.
Just wait, it gets better.
There's more.
Oh, yeah. The paper then connects them to this really fascinating concept, the Poisson sigma model.
Okay, you're going to have to break that one down for me.
Fasten your seatbelt, because we're about to jump into the realm of quantum field theory.
Here we go.
Now, instead of just thinking about a single particle moving through space, imagine trying to describe how a whole field changes over time.
Like an electromagnetic field.
Exactly. Or a gravitational field.
Got it.
The sigma model part is all about describing the behavior of these fields in the quantum world.
Okay.
But the really interesting bit is the Poisson aspect.
What about it?
Remember those Poisson brackets we might have vaguely touched upon before?
To be honest, those are a bit fuzzy in my memory.
Okay, the main thing to remember is that they basically tell us how different quantities in classical mechanics are related to each other.
Like position and momentum, for example.
Yeah. Exactly. Now, what the Poisson sigma model does is it brings those Poisson brackets, which are fundamental to classical mechanics, into the wild world of quantum field theory.
So we're taking something from classical physics and injecting it into the quantum realm.
Exactly. And the amazing thing is that this Poisson sigma model turns out to be deeply intertwined with these coherent state path integrals.
It's like they're two sides of the same coin, offering different but complementary views of the same underlying physics.
That's a great way to put it. It's like they're speaking the same language, just with different accents.
I love that analogy. This is really making me appreciate how interconnected physics is, how all these different concepts are woven together.
It's truly remarkable.
So, am I understanding this correctly? This paper is saying that these coherent state path integrals, which seem pretty abstract at first, they're directly linked to this whole other domain of physics, quantum field theory.
You got it. And not just any quantum field theory, one that's been a major focus of research for decades.
Wow, it's like finding a hidden passageway between two seemingly separate worlds.
That's a fantastic way to describe it. It's like discovering a secret bridge between two islands of knowledge.
And speaking of connections, the paper also digs into some fascinating details about the uniqueness, or I guess I should say the non-uniqueness, of these path integral solutions.
Right, we touched on that earlier, how you can have multiple solutions that all seem to work.
Exactly. It's like the math is giving us different possible interpretations of the same physical event.
And this is where the paper's emphasis on mathematical precision really shines.
How so?
It goes to great lengths to show how these different solutions actually arise from different choices we make in how we set up the problem mathematically.
So it's not that one solution is right and the others are wrong. It's more about recognizing that the answers we get depend on the specific lens we're using to view the problem.
Exactly. It's about understanding the limitations and the nuances of the mathematical tools we're using.
That makes a lot of sense. It highlights the deep and often subtle relationship between math and physics.
Absolutely. The math isn't just some abstract tool. It's a language that's revealing profound truths about the universe itself. And in this case, it's guiding our intuition, helping us to see the quantum world in a whole new light.
It really is amazing how something as seemingly abstract as mathematical rigor can lead to such profound insights about the nature of reality.
It is, isn't it? And that's what makes this whole field so incredibly exciting.
I couldn't agree more.
It's a journey of constant discovery, and papers like this one, they're like signposts pointing us towards new and uncharted territories.
I'm ready for the adventure. Speaking of those aha moments, we should definitely circle back to the Bergman kernel.
Oh, yes. The Bergman kernel is crucial to all of this.
You mentioned before that it's like a key unlocking information about those Kähler manifolds.
Right. It is.
But how does that actually work? Like, what's going on behind the scenes?
Well, it all comes down to how the Bergman kernel encodes geometric information, but in a way that's directly relevant to quantum mechanics.
Okay, I'm following so far.
Think about it like this. Each Kähler manifold has its own unique fingerprint, and that fingerprint is encoded by its Bergman kernel.
Interesting.
And this fingerprint, which we often call a metric, it's what lets us measure distances and angles within this abstract space.
So it's like the Bergman kernel provides us with a set of customized tools for navigating those manifolds.
Exactly. It gives us the right kind of ruler and protractor for the job.
Huh, that's pretty cool.
And the really fascinating part is that those distances and angles, they directly correspond to things like probabilities and interferences between quantum states.
So the geometry of the space is intimately connected to the behavior of the quantum system.
Precisely. And when this Bergman kernel has certain special properties, like being constant along the diagonal, as the paper mentions, it can make those really complex path integral calculations much, much simpler.
I remember us briefly mentioning that concept of constant along the diagonal earlier, but I'll be honest, it's still a bit fuzzy for me.
Yeah, it's a bit of a mind bender.
Can you maybe give us a more intuitive grasp of what that actually means?
Okay, so imagine plotting all the points of our Kähler manifold on a graph, right?
Okay, got it.
Now, the diagonal of that graph represents all the points where something is basically being compared to itself.
Right, like a points relationship to itself.
Exactly. When the Bergman kernel is constant along that diagonal, it tells us that every single point in our quantum space has this perfect self-correlation.
So each point on the map knows exactly where it stands, so to speak.
Yes, precisely. There's no ambiguity, no uncertainty about its properties.
It's like each point has a clear and well-defined identity within that space.
You got it. And this kind of clarity, where the Bergman kernel is behaving so nicely, it turns out to be surprisingly common in a lot of important quantum systems.
Really?
Yeah, which makes you wonder if there's something deeper going on here. You know, it's like the universe has this inherent preference for elegance, even at the most fundamental level.
It's all connected, isn't it? The elegance of the math, the strangeness of the quantum world, the way this paper ties together all these seemingly disparate concepts.
It really is quite beautiful, isn't it?
Absolutely. It's like we're glimpsing the intricate tapestry of reality, seeing how all the threads are woven together.
That's a wonderful way to put it. And to think we haven't even scratched the surface.
I know, right? This deep dive has already been such a wild ride, and we've only just begun exploring this amazing world of coherent state path integrals.
And trust me, the journey only gets more exciting from here.
Well, in that case, I can't wait to dive back in. Yeah. It's like we're trying to uncover the hidden blueprint behind those quantum paths.
Precisely. But here's the catch, and the paper actually points this out too.
What's the catch?
This analogy, while helpful, it has its limitations.
How so?
Well, think about a typical antiderivative problem.
Okay.
Usually there's just one right answer, right?
Yeah, that's kind of the point.
But path integrals, they're not as straightforward. You can actually end up with multiple solutions that seem perfectly valid, which makes things a bit tricky when we try to interpret what the math is telling us about reality.
So it's not that the math is wrong, it's just that it might offer us different equally valid perspectives on the same quantum phenomenon.
That's the heart of it. It's like looking through a kaleidoscope. You see different patterns depending on how you turn it, but they're all generated by the same underlying structure.
Wow, that's a really cool way to visualize it.
And to make things even more interesting, the paper actually highlights how important the second derivative is in all of this.
The second derivative. Now we're really going deep into calculus territory.
I know, right? But there's a good reason for it.
I hope so.
It turns out that to get the right answer, we need to go beyond just the first derivative and really delve into what the second derivative is telling us.
And what exactly is the second derivative telling us in this context?
That's the really intriguing part. It hints at the strangeness of the quantum world.
How so?
Well, in your normal calculus class, the second derivative tells you about the curvature of a function, right? How much it's bending.
Right, like how much a curve is curving.
Exactly. But here, it's suggesting something much weirder.
Like what?
The paths we're dealing with, they're not those smooth curves you see in textbooks.
They're not?
No, they're more like jagged, fractal-like lines that are constantly changing direction.
So the second derivative helps us capture that quantumness, that inherent jitteriness of the quantum world.
Exactly. And it's this inherent strangeness that makes this whole area of physics so captivating.
I can definitely see why. So we've got these coherent state path integrals,
and
they're already bending our minds.
Just wait, it gets better.
There's more.
Oh yeah, the paper then connects them to this really fascinating concept, the Poisson sigma model.
Okay, you're gonna have to break that one down for me.
Fasten your seatbelt because we're about to jump into the realm of quantum field theory.
Here we go.
Now, instead of just thinking about a single particle moving through space, imagine trying to describe how a whole field changes over time.
Like an electromagnetic field.
Exactly. Or a gravitational field.
Got it.
The sigma model part is all about describing the behavior of these fields in the quantum world.
Okay.
But the really interesting bit is the Poisson aspect.
What about it?
Remember those Poisson brackets we might have vaguely touched upon before?
To be honest, those are a bit fuzzy in my memory.
Okay, the main thing to remember is that they basically tell us how different quantities in classical mechanics are related to each other.
Like position and momentum, for example.
Exactly. Now, what the Poisson sigma model does is it brings those Poisson brackets, which are fundamental to classical mechanics, into the wild world of quantum field theory.
So we're taking something from classical physics and injecting it into the quantum realm.
Exactly. And the amazing thing is that this Poisson sigma model turns out to be deeply intertwined with these coherent state path integrals.
It's like they're two sides of the same coin, offering different but complementary views of the same underlying physics.
That's a great way to put it. It's like they're speaking the same language, just with different accents.
I love that analogy. This is really making me appreciate how interconnected physics is, how all these different concepts are woven together.
It's truly remarkable.
So am I understanding this correctly? This paper is saying that these coherent state path integrals, which seemed pretty abstract at first, they're directly linked to this whole other domain of physics, quantum field theory.
You got it. And not just any quantum field theory, but one that's been a major focus of research for decades.
Wow, it's like finding a hidden passageway between two seemingly separate worlds.
That's a fantastic way to describe it. It's like discovering a secret bridge between two islands of knowledge.
And speaking of connections, the paper also digs into some fascinating details about the uniqueness, or I guess I should say the non-uniqueness, of these path integral solutions.
Right. We touched on that earlier, how you can have multiple solutions that all seem to work.
Exactly. It's like the math is giving us different possible interpretations of the same physical event.
And this is where the paper's emphasis on mathematical precision really shines.
How so?
It goes to great lengths to show how these different solutions actually arise from different choices we make in how we set up the problem mathematically.
So it's not that one solution is right and the others are wrong. It's more about recognizing that the answers we get depend on the specific lens we're using to view the problem.
Exactly. It's about understanding the limitations and the nuances of the mathematical tools we're using.
That makes a lot of sense. It highlights the deep and often subtle relationship between math and physics.
Absolutely. The math isn't just some abstract tool. It's a language that's revealing profound truths about the universe itself. And in this case, it's guiding our intuition, helping us to see the quantum world in a whole new light.
It really is amazing how something as seemingly abstract as mathematical rigor can lead to such profound insights about the nature of reality.
It is, isn't it? And that's what makes this whole field so incredibly exciting.
I couldn't agree more.
It's a journey of constant discovery, and papers like this one, they're like signposts pointing us towards new and uncharted territories.
I'm ready for the adventure. Speaking of those aha moments, we should definitely circle back to the Bergman kernel.
Oh, yes. The Bergman kernel is crucial to all of this.
You mentioned before that it's like a key unlocking information about those Kähler manifolds.
Right, it is.
But how does that actually work? Like, what's going on behind the scenes?
Well, it all comes down to how the Bergman kernel encodes geometric information, but in a way that's directly relevant to quantum mechanics.
Okay, I'm following so far.
Think about it like this. Each Kähler manifold has its own unique fingerprint, and that fingerprint is encoded by its Bergman kernel.
Interesting.
And this fingerprint, which we often call a metric, it's what lets us measure distances and angles within this abstract space.
So it's like the Bergman kernel provides us with a set of customized tools for navigating those manifolds.
Exactly. It gives us the right kind of ruler and protractor for the job.
That's pretty cool.
And the really fascinating part is that those distances and angles, they directly correspond to things like probabilities and interferences between quantum states.
So the geometry of the space is intimately connected to the behavior of the quantum system.
Precisely. And when this Bergman kernel has certain special properties, like being constant along the diagonal, as the paper mentions, it can make those really complex path integral calculations much, much simpler.
I remember us briefly mentioning that concept of constant along the diagonal earlier, but I'll be honest, it's still a bit fuzzy for me.
Yeah, it's a bit of a mind bender.
Can you maybe give us a more intuitive grasp of what that actually means?
Okay, so imagine plotting all the points of our Kähler manifold on a graph.
Okay, got it.
Now, the diagonal of that graph represents all the points where something is basically being compared to itself.
Right, like a points relationship to itself.
Exactly. When the Bergman kernel is constant along that diagonal, it tells us that every single point in our quantum space has this perfect self-correlation.
So each point on the map knows exactly where it stands, so to speak.
Yes,
Yeah.
Precisely. There's no ambiguity, no uncertainty about its properties.
It's like each point has a clear and well-defined identity within that space.
You got it. And this kind of clarity, where the Bergman kernel is behaving so nicely, it turns out to be surprisingly common in a lot of important quantum systems. Yeah, which makes you wonder if there's something deeper going on here, you know? It's like the universe has this inherent preference for elegance, even at the most fundamental level.
It's all connected, isn't it? The elegance of the math, the strangeness of the quantum world, the way this paper ties together all these seemingly disparate concepts.
It really is quite beautiful, isn't it?
Absolutely. It's like we're glimpsing the intricate tapestry of reality, seeing how all the threads are woven together.
That's a wonderful way to put it. And to think, we haven't even scratched the surface.
I know, right? This deep dive has already been such a wild ride, and we've only just begun exploring this amazing world of coherent state path integrals.
And trust me, the journey only gets more exciting from here.
Well, in that case, I can't wait to dive back in. But before we get too far ahead of ourselves, let's talk about the physical implications of all this.
Right, because we've been mainly focused on the mathematical framework so far.
Exactly. This paper lays out this really elegant mathematical foundation for these coherent state path integrals.
It does.
But what does it all mean for our understanding of how the quantum world actually works?
That's the million-dollar question, isn't it?
It really is. I mean, does this change how we interpret quantum mechanics itself? Does it give us new tools for solving problems in quantum physics?
Those are some really deep questions, and to be honest, we're only just beginning to scratch the surface.
So this paper is more like opening a door to a whole new realm of possibilities rather than providing all the answers.
Exactly. It's like we've discovered a new continent, but we've only explored a tiny fraction of its coastline.
That's a great analogy. It really highlights how much more there is to learn and discover in this field.
It does, and that's what makes it so exciting.
I totally agree. This paper's given us a lot to think about, that's for sure.
It has, and I think it's a testament to the power of taking a rigorous mathematical approach to these really fundamental questions in physics.
Absolutely. We've journeyed from the basics of path integrals all the way to the intricacies of Kähler manifolds and the Bergman kernel.
And we've even touched upon those mind-bending concepts like the second derivative and the Poisson sigma model.
It's been quite a ride, but I have a feeling this is just the beginning of an even bigger adventure.
Oh, I think you're right about that.
Well, on that note, a huge thank you to you for guiding us through this fascinating deep dive into the world of coherent state path integrals.
My pleasure. It's always a treat to talk about this stuff.
And to our listeners, thank you for joining us on this incredible journey into the quantum realm. We hope you found it as mind-expanding as we did.
Until next time.
Keep those questions coming.